Good morning, ladies and gentlemen. Good morning, ladies and gentlemen. You are welcome to the day 2 of Faculty of Technology International Conference. It is my delight to welcome you here this morning. My name is Elufo Fisayo. I am from the Department of Civil Engineering.
Recording in progress.
I welcome each and every one of you. Without wasting time this morning, because time is fast spent, I will like to recognize and welcome to the high table the chairman of this morning's plenary session and president of Professor M.O. Adiri of the Department of Material Science and Engineering of Afemi Awolowo University. Professor, you are welcome, sir. Good morning, sir. Also, to be working with him closely at the plenary and technical session for this morning are Professor S.O. Obayopo of the Department of Mechanical Engineering and Dr. O.O. of the Department of Material Science and Engineering of Afemi Awolowo University. Please put your hands together for them. Professor Obayopo will join us shortly. This morning's program is in 2 parts. We will have the plenary session and the technical session. But we're going to start with the plenary session this morning. And to speak to us at this plenary session is Dr. Wolfram Schmidt from Berlin, Germany. He will be speaking to us on the title, Building Materials Technology in Times of Climate Change, How Conscious Use of Materials Can Mitigate Societal and Environmental Challenges. But before he speaks to us, it is very important for us to get to know who Dr. Wolfram is. And it's my pleasure to invite this morning Dr. Mrs. Ayodele to read to us the citation of Dr. Wolfram's speech. Thank you very much.
All right. Thank you very much. I'm standing on the existing protocol. Dr. Wolfram, you are welcome to our midst. It's a pleasure to have you here. I hope you are hearing us.
Yes, I can hear you.
Oh, all right. Thank you very much. So I'm here to read the citation of Dr. Wolfram, our plenary lead speaker for this morning. There are some German words there. I might not be able to pronounce them very well, but just bear with me. So Dr. Wolfram Schmidt works in the Department Safety of Structures at the BAM, Berlin, Germany, and is responsible for the rheology and admixtures laboratory with focus on particle polymer fluid interactions and sustainable, innovative organic and mineral cement and concrete constituents. Furthermore, Dr. Wolfram is board member of the German Rheological Society and chairman of the RILEM Development Advisory Committee. He is founder of the Pan-Africa Cement Round Robin PACE PTS and initiator of the conferences Advances in Cement and Concrete Technology in Africa and ISEE Africa, that is Innovation, Science and Engineering Education. With his colleague, Kolawole Olonode, who is in UNILAG, he received the German African Innovation Incentive Award, GAIIA, for developing cementitious binders and chemical admixtures from waste of cassava production. His research and educational projects focus on potentials for more sustainable, equitable, circular urban construction using local, environmentally friendly resources. He is also involved in activities related to sustainable construction by the United Nations organizations and the Global Consensus on Sustainability in the Built Environment. So ladies and gentlemen, I present to you Dr. Wolfram Schmidt, who is the lead speaker for this plenary session. Please, let's put our hands together for him. Thank you.
I guess you can see my screen now.
Yeah.
And I hope that I can start with my talk. Thank you very much for the nice introduction and for the great opportunity to be here to give quite a long talk about building materials technologies in times of climate change and how conscious use of materials can mitigate societal and environmental challenges. An introduction was made, so without further ado, I will start with the presentation. And obviously my screen does not work at the moment. Let me see. And let's start with a short history of civil engineering, because often civil engineers are somewhat quite important for societies, but they are not aware about the importance of their profession. And therefore, I think it makes sense to look back a little bit in the history and look at how human beings have always been building. I mean, we've been building since we ever existed. And in the beginning, we had people who built their houses. They also developed them forward. They were crafters. Later, over the course of the centuries, a profile was built which was called a master builder. These were outstanding people who were a blend of architects and what civil engineers do today, but they also had to be aware about history, about religion, about culture, about arts, about tradition, in order to please their donors and also to please the society in which they were operating. And that happened to happen for many, many centuries until the profile of an engineer was formed for the very first time, which was combining technical and mathematical and scientific skills in a more model-based, in a more equation-based, in a more technical approach. And these first engineers that popped up on this planet as a job profile were actually war engineers. They were developing machines to fight others, and they were developing the defense structures to protect people from these wars. So the first engineers were war engineers, and only a couple of centuries later, in the 19th century, or maybe in the 18th century, the first engineers popped up that were considered to be civil engineers, as people understood that the engineering of war could also be used in a civil environment. And that is something very important to understand. So we are civil engineers, and the word civil is something very important in our profile. We are the good ones, actually. So civil engineering classically combines materials, and these materials are taken, harvested, and they are converted and put into new structures. That's the classical profile of a civil engineer. But if you consider that materials and structures are heavily interlinked, so the materials determine the properties of a structure, and the structures determine the demand for materials that is required. And then, in the meantime, we also know that materials require resources, and this requires processing, and that has a strong impact on the climate. Hence, working with materials has an impact on the environment. But also, if you build structures, this has an impact on how human beings interact, how they are connected, how inclusive they are living. So building structures also has implications for societies and economies. And then again, the environment, the bigger circle, and society and the economy are also interlinked by the environment determining the well-being of the society, and the economy and the society determining the consumption of materials and resources that come from the environment. So in this very, very complex problem area, civil engineers are pivotal. And we are not aware of that. The classical civil engineering is literally focused on materials and structures. That's our comfort zone. This is where we have equations, where we have standards, where we have technologies. And in the past, let's say 20, maybe 30 years, we have also identified, mostly on political pressure and also on the fact that research funding is getting into that direction, that it's more important to understand how materials affect the climate particularly and the environment. So here we have been developing a little bit of knowledge over the past decades. And just in recent years, we identified that already the structural setup, the structural design has an impact on the environment. This is a slowly increasing awareness, but what we are not at all aware of is that this entire area of structures and materials, how they affect the environment, also has social and economic implications. We are not aware of that. And that is a mistake because, you know, in music, like Bridge Over Troubled Waters, or in literature, like Pillars of the Earth, or in religion, like the Tower of Babylon, civil engineering structures have always been a central element of our culture, no matter what we look at, since millennia. And as civil engineers, we also have a dramatic impact on our society. We just have to be aware of that. Whether we build a bridge and we connect the people, or whether we build a wall to separate people or to keep people out, is a big difference. And unfortunately, these days, we are building more walls than we are building bridges. And one of the facts is that civil engineers do not play a role in our society at all. We are not used to raise our voices. We are like, if we would express it in a music band, we are like the bassists. Without the bassist, all the music would not sound good. But the bassist, as you can see it here on the figure, is always in the shade. The bassist is not seen. The bassist is just running the systems behind, but he's not raising a loud voice or getting very strong. And just as an example, if I look at the German parliament, we have 700 something delegates in the parliament. Only 20 of them are engineers, and only 3 of them are civil engineers. So we do not fulfill the demand of the society to have a greater impact on what we're doing. We just perceive ourselves as those who are standing in the back and do our mathematics. And that one of the main responsible aspects in that is that our curriculum, when we are going to the university, continues to teach us to be a civil engineer as we used to be 120 years ago. Like 120 years ago, a civil engineer mostly had to be good in physics and in calculating. Everything else was quite unimportant. The most important thing was that on the bottom line, there was a result that was safe enough to let the structure hold. But then over the course of the years, the profile of a civil engineer has dramatically changed. Mathematics are not of importance anymore. I don't want to say they are not of importance anymore. They are extremely important, and it's also important to understand the fundamentals behind it. But the technical aspect of making the calculus can be done by a computer today. Every mobile phone can calculate better than a human being. So what has changed is that we have to deal with computational methods, we have to use information technologies, organization, economics, and law have become much more important, but our universities continue to teach us to be a civil engineer as we were 120 years ago. And if you can see in this figure on the bottom, the bottom figure, which is related to the materials, particularly the materials have become much more important. In the past we had a limited number of materials with a limited variety of performances, but today every single material it's a whole universe, and that is not reflected in our curricula, which is much more focused on the structural part of it. And that is so important because, you know, our technology has evolved, and we do know that we have technologies to reduce the energy demand and to reduce the carbon footprint. But what we don't have is tools to avoid materials use. So in the near future, there will be huge urbanization processes happening all over the world with a very, very strong influence in Africa, and that inevitably requires materials. We can have the best technology to reduce our consumption, but the materials are still required to build our structures. And this is what we have to see, and that will be the challenge of the next decades to solve. Now let's discuss a little bit about materials. If we think about structural materials that could also be used in an urban framework for the larger scale, we would have concrete, we have steel, we would have soil-based materials, and we would have timber. And well, all of them have their pros and cons. I wouldn't want to say any of them is better or worse, but we have to discuss them and we have to use them in a reasonable way. So let's first of all look at their performances, and just imagine that we would use these materials, soil, concrete, steel, and timber, and we would just stack it upon each other and see how high the tower would be in terms of expressed in kilometers. So the soil tower would just be 100 meters high. That's it. The concrete tower would probably be 2.1 kilometer high. That's quite impressive already. Steel would already be 6.5 kilometers, because steel has these outstanding properties in terms of strength. And timber would even be 9.3 kilometers high, considering only the vertical load, certainly. You cannot build that high with timber, but the reason for that is that timber has a relatively low density as in comparison to the strength it has. So from this perspective, we would say let's opt for timber or steel, but we also have to see what the carbon footprints of these materials are. So soil has an extraordinarily low carbon footprint. Concrete has a higher footprint, and steel has an extremely high carbon footprint. So we have to use that with a lot of care, and eventually timber also has a relatively low carbon footprint. So if we look at the carbon footprint of timber, and if we look at the strength it could provide in certain structural designs, we could possibly assume that timber might be the best possible solution that we have at the moment. But even here, we have to be extremely careful. Let's think about how what's happening when a tree grows. Like in this figure, you can see that while the tree grows, it consumes CO2 from the atmosphere. So in the middle part of this figure, you can see that in combination with the solar energy, when the tree grows, it consumes CO2 from the atmosphere, and it requires H2O, water from the soil. And this together, in the process of photosynthesis, is converted into glucose, mostly stored in starch and cellulose, and also oxygen is given back to the atmosphere. So that's the way our trees consume the carbon emissions that, for example, we as human beings produce from just digesting. But then, when a tree has reached its end of life and it's deteriorating again, all these carbon emissions are released into the atmosphere again. So when a tree has grown and a tree has completely diminished by being converted into soil, into animals, into whatever gases, the tree is more or less carbon neutral. So that's what people think makes building with timber very sustainable. So you can see this figure that I've shown on the top left, a bit smaller, and then let's assume halfway, when the tree has not reached its end of life, but maybe half of its end of life, you take the tree, you cut it, and then you put it into a house. Then you can see that there is a CO2 negative effect of the tree, which means the climate is released due to that. So this carbon that the tree has sequestered upon growth is now stored in the house. Looks very nice, but certainly we want to build another tree after we cut a tree. So we grow another tree next to the house, and then this tree continues to grow and sequester carbon over the course of time, which means the curve continues and is very comparable to what you can see on the top left curve, which would be the natural cycle. However, then we can cut the tree again, and we can play the game again and again and again, and build another house. But earlier or later, these houses have to be torn down. And then what's happening with the tree? What's happening with the timber? It's going to be burned, it's going to be deteriorated, whatever is happening. After the end of the life, the carbon that is stored in that house will be released. Which means at the end of the day, we will be as carbon neutral as we were before, just with a certain delay in time of 50 to 100 years, which is the lifetime of the building. If we want to build another tree, then, or if we want to grow another tree, then it's better to grow this other tree in addition to a tree which is not converted into a house, because then you can see on the top left that then the carbon sequestering effect of one tree and another tree is adding up. So one tree is continuing to grow, another tree is continuing to grow, and we have a much higher carbon sequestering effect. And then certainly when one of the trees has reached its end of life, it starts to deteriorate again, And that is the moment where the tree becomes climate burdening again. And that would be the right time to use this biomass and convert it into something. But I will come back to this later. So what we can say is that a single human being emits approximately 360,000 tons of carbon in a lifetime. And the tree sequesters approximately 22 kilograms per year. So you can calculate that a single human being requires 16,000 trees to offset the carbon emissions that we produce during our lifetime. A single human being requires 16,000 trees. And every year we lose 10 to 15 billion trees on this planet. We only have approximately a third to half of the trees that were on this planet before human beings existed. So when we consider CO2 and climate change as a global problem, it's not enough to say that in some countries we have a lot of trees, and here is very, very sustainable to build with trees. Like on the figure on the right side, you can see that in some countries we have something like a gain in trees. But on a global scale, if you look at that figure, so the green ones are the gains of trees, and the red ones are the losses of trees. The losses of trees on a global scale are so much higher than the gains in some particular regions on this earth. So before we do not end up in a net plus, in a net gain of trees, we should be very careful in using timber in construction. Now, okay, I talked a lot about timber because that becomes important later. Again, I will be shorter with steel. So we do know that steel is extremely carbon intensive, but certainly steel has also outstanding low deflection behavior. It has a very good elastic behavior. It can deform, it can absorb a lot of deformation energy in the elastic state, but particularly also in the plastic state. So steel gives us a lot of safety when it comes to dynamic loading, which is a big issue when it comes to large deformation. So steel is inevitable, and with recycling steel that we are using more and more, the carbon footprint can be significantly reduced. And many, many concrete applications actually, because we use steel reinforced concrete, would not be possible without the steel. So also concrete will lose its performance without the synergy with steel. And approximately 25% of steel production globally is for reinforcement, for reinforced concrete steel structure. So steel has a high carbon footprint, but it's also inevitable. Then let's talk about soil, earth-based materials. There are beautiful examples of wonderful architecture using earth-based materials, like the Great Mosque in Genève, for example. It has an extraordinary low carbon footprint. Sure, we just take what is on the ground and we reform it. But the problem is that a lot of maintenance is required. Like the mosque in Genève is regularly maintained by people who celebrate around the mosque, and they come together for all kinds of affairs, and in this context they also maintain the mosque. But if you think about big cities, that would never work with the maintenance, and that is the problem, that people, in order to avoid the maintenance of these structures, they put cement into the soil. And here they typically use something like 5 to 10% of the dry mass of the materials. The expected compressive strength would be something like 1.5 to 2.5 megapascals, which is very, very low. So we use a very high amount of cement for a very, very low strength here, which means we completely underuse such a high carbon emission material as cement. If we would use the same amount of cement and put it into real concrete, we would achieve something like 50 to 25 megapascals. So we have to very carefully also discuss the topic of using soil-based materials, because without cement, they are very, very green. But if we use cement-stabilized soil-based materials, that can become a burden, because we have to reduce the cement consumption worldwide. And that's the next topic, which is concrete. And a major contribution to the carbon footprint of concrete is actually the cement. It makes about 85 to 90% of the carbon emissions. And about 40% of the carbon emissions from cement are coming from the operation of the cement factory, from the high temperature, 1,450 degrees Celsius is required to burn it, and also for transportation, grinding, and so on and so forth. But here we can't really optimize anything anymore, because those cement factories, the modern ones, are operating at very, very high efficiency level. And another 60%, if we think about Portland cement as a binder, are coming from the decomposition of limestone. So we have to convert calcium carbonate into calcium oxide, and what is released in this process is CO2. It's just an inherent chemical aspect of the processing of cement. So when we have burned our clinker, which finally becomes the reactive material for cement as a binder in concrete, we require something about 65% calcium oxide quicklime. We require about 25% silica and about less than 10% alumina, which we get from limestone, clay, and other sources of alumina and silica, like bauxite, for example, and other. We use various silica sources. But there are certainly also other binder chemistries possible. So we have an established cement chemistry, which is the ordinary Portland cement, and we can put it into such a ternary diagram where on the left side you can see from 0 to 100% calcium oxide. On the bottom you can see the alumina, and on the right side you can see the silica, and we have about these 65% calcium oxide. We've got actually something like 10% alumina, and we've got 25% silica. That is the chemistry where we are looking at. But then we have a lot of alternative binder systems which function in a very similar way, like for example geopolymers that do not require any calcium at all. They require silica and alumina. We also have calcium sulfoaluminate cements, which have a different chemistry, and we also have high alumina cement types which are operating more in this area. So this entire triangle can be made useful as cementitious binder technologies. We are just focusing so much on this ordinary Portland cement range. But they all can be binder, and the final product would be concrete. Now, in order to replace this high CO2 emission ordinary Portland cement, we use extenders or reactive materials like silica fume, like fly ashes, like ground granulated blast furnace slag, metakaolin, or also lime to get a good binder done, so that at the end of the day the whole range of cements which can be found on the market are actually in this area. But we have to see that those materials which we can use for blending actually are not the only materials that are available. These are the only materials globally that are available at large scale. And that is the reason why we use it. But we could use also completely different materials coming from municipal waste, mining waste, agricultural waste, aquacultural waste, and industrial waste, which would also have a very similar chemistry. We just don't use it because it's not attractive at the moment to use it, because it's only available at small scale, but we'll also come back to this later. So what we can conclude from here is that all materials have their pros and their cons. And I think that the future of materials use will be that we build much more hybrid. Like this beautiful building that is, I've taken this picture in Zanzibar, Tanzania. The Kiswahili architecture uses a lot of hybrid elements, mixing timber with plaster, with lime, bricks, and other materials together in such a way that the strength of the materials are strengthened and that the weaknesses of the materials are avoided as best as possible. So hybrid materials use, not composite, because composite materials always means when we recycle it, we have to separate the different parts. But if we use the materials according to their strength and not according to their weaknesses, the hybrid materials use is absolutely favorable in the future. But whatever materials we are going to use in the future, there's one material that is standing out, which is concrete. And this figure shows why. here on the left side, you can see the mass of concrete that we're producing globally. So these are the global numbers in comparison to the materials that to all the different materials. So this entire range here is the mass of concrete we produce. And even if we look at it from a volume perspective, this entire volume is in comparison to this fraction is what we produce as concrete for the world. And here, by the way, you can see the carbon emissions resulting from this concrete use, and it's relatively low in comparison to the mass or the volume we're producing. But what is even more important, and that's the reason why concrete is here to stay, is that there is nothing available on this planet that could replace this huge amount of materials by any chance. We don't have any other resources available for that. So if we like it or if we don't like it, we have to live with concrete. Now let's take a closer look into concrete and cement and what it means for our societies. So if we think about those societal challenges that we face these days, like habitat, like infrastructure, like urbanization, like environmental pollution, and the consequent resource depletion from our consumption, then we see that concrete plays a pivotal role in all those challenges that we need to solve, because concrete is responsible for most of these challenges. Concrete is 50% of everything that human beings have ever produced on this planet since their existence. It's the second most widely used material after water. So there's nothing we consume more, except for water, than concrete. And that is the reason why it is a huge environmental challenge. And the carbon emissions resulting from concrete are in the order of magnitude of 10% of the total carbon emissions that humans produce. But then again, if we consider that concrete is such a high fraction of everything that we produce, then if we only make small changes, we can have a huge leverage on the climate of our planet. So if concrete is 50% of everything that we've ever produced, then even a small change can be much more than a much larger change percentage in a less heavily consumed material. And after all, we have to see that concrete is made of those minerals or those elements that we find on the outer crust of our Earth. So we've got something like 98% of the elements that we can find in the outer crust of the Earth are just 8 elements. And concrete is made of these 8 elements. It would be an illusion to believe that our future cities will be built of those 2% that complement. So we do not have an alternative to concrete. The only alternative that we do have to concrete is building better concrete, which is greener, which is more efficient, which uses less binder, and which can be used with less materials in the overall structure. That's the way forward. And if we want to become better, we probably have to reconsider the business model that frames the concrete technology. And I like to use this figure, even though I do know that in Nigeria it is not, it doesn't have the same meaning as it has in Germany. So in Germany we do not grow avocados. We import avocados, mostly from South America. And avocados are perceived in Europe as a superfood, which contain everything that is required, that make you healthy, strong. So it's an amazing piece of food, everything in one single fruit. And that's the reason why we love avocado, but we also do know that it's not sustainable because we have to import it from far away, and that increases the carbon footprint. The reality is, despite the fact that avocado has been established as a superfood in Europe, there would be many alternatives, as you can see on the right side, how we could replace avocado entirely. Just the complexity of the system would become a little bit more sophisticated, so we have to cut a whole lot of different vegetables in order to achieve the same performance as the avocado, but it is possible. And that's the way how we can change our mindset by looking more into the regional scale and find better ways to replace what has been established so far, but which is not healthy. So, therefore, I would like to talk more about the need to localize supply chains for the construction industry. Here you can see a figure of the different fractions that make our concrete. So on the top we will find Portland cement. If we think in a very classical way, we have some admixtures to reduce the water content. We have to add some water, and then we have a big fraction of sand and aggregates. Now, as mentioned earlier, Portland cement makes out about 85 to 90% of the carbon footprint. So that's where we have to work at. And what we do is that we try to replace the Portland cement with those supplementary cementitious materials that I mentioned earlier. So we can do that blending of Portland cement and supplementary cementitious materials to make the binder greener. We can do this on the large scale in a cement factory. But we can also buy the ordinary Portland cement and do the blending while we are mixing the concrete with water and sand and aggregates and so on. Anyway, we can do this in the precast factory or in the ready-mix factory or on the construction site as well. So these are the two business models, I would say. One is blending of business models behind reducing the carbon footprint of cement. One is blending the concrete in the cement factory, and one is blending concrete in the concrete factory or on the construction site. So blending greener binder in the cement factory, because cement factories produce at a very large throughput, they need materials that are available in huge supply streams. And that limits the number of options of materials we can use to blend the cement. While, if we would blend the cement in the concrete factory or on the construction site, we could use much smaller supply streams. So we would have nearly unlimited options to make a better binder and make a better concrete. But this is what we are doing today, what our standards are about, what our technology is about, what our lecturing is about at universities. It's all about using the cements that were pre-blended in the cement factory. And if you look at the circles, and what would be the business for the cement industry, well, you can imagine that the cement industry is very much in favor of the left business model because they can sell much more of their binder. It's very clear that the cement industry doesn't want to change anything in the existing system because this one would bring much more benefit back to the local economy. And that's the reason why in our standards we're always looking at the cement factories. And if we take a look at the standards, and I've been collaborating with a lot of colleagues in the standardization area in Africa, I identify that a lot of European standards are applied in African countries. But we have to see that the history of cement since its invention, already in the Roman Empire, it has been a European technology history since ever. It came to sub-Saharan Africa very late. Today we can see a lot of cement factories popping up because certainly all the global investors, they see a big business potential on the African continent. But the problem by applying the European standards and the European technology history is that everything that we apply is looking at European climate, European industries, European geology, European stakeholders, European infrastructure, and the European price structures. And that is the reason why we have limited our binders to 39 different cement types in terrible tables to be used. But all those materials that are allowed to be used in our European concrete framework are those which are based on the European industrial history. Energy and steel production are the industries behind it. But more than 65% of the cements that are standardized in the European standards have no relevance in Africa at all because those materials are not available on the continent. It makes a lot of sense that we did this way in Europe because we have a very high density of cement factories and we have a very good limestone also in Europe. So on the left side you can see only for the European countries and Switzerland that we have a whole lot of cement factories on the ground. But on the same square area, where in EU countries plus Switzerland, you find 8 cement factories, in Africa you only find a single cement factory. So the density of factories is much lower, and also in this part of Europe, we are much more heavily populated. So the population density is nearly 3 times as high as it is in Africa, which means also the customers, the consumers of the cement and concrete are much more complicated to access in an African framework. So, and that has implications, I mean, on prices and on everything. In Europe, for example, cement prices, people are complaining that they are high, but actually they are low. So all our standards are made for reducing the labor cost. Labor cost is our highest cost fraction in our calculations. And therefore, everything tries to reduce the labor cost as much as possible. But in an African context, cement prices are terribly high, and the labor cost for working on construction sites is relatively low. And that causes that the price differences are much different, and cement is relatively to the purchasing power of the different countries much more expensive in Africa. So I just made a comparison of the, let's say, the price paying that a cubic meter of concrete would cost for a German if I would convert the price and income structure. Suddenly we would find out that the cubic meter of concrete, which an average German, not an average, but which would be 100 euros in Germany, converted to the Ghanaian price structure, would end up in 2,000 euros per cubic meter of concrete, 20 times more. And certainly you can imagine that the standards in Europe would be different. That would be the price structure. But certainly there are many more differences, like bagged market versus silo market. In Germany, I think the bagged market is less than 2% of the overall market. So everything comes in silos. We have a lot of precast and ready-mixed here. In Africa, mostly I see side-mixed concrete. The geology is different, the geography, the climate, and then also the issue of the informal construction business is much more relevant, with about 80% of the construction business on average in Africa. So technically and economically, European regulations do not make sense in Africa. So new regulations would be required that would also support the sustainability. And one way forward that has to be accelerated in an African context would be to work much more with precast plants or ready-mixed factories to reduce the carbon footprint of concrete. So if the density of cement factories is so low, then let's do the blending in the concrete factory. Here we can use regional materials, we can use materials, we can partner up with the local industries and find cement replacements which are in the neighborhood, and this can be provided finally to the customer with a significantly lower carbon footprint. That's the way forward for Africa, for the structure of Africa, for the infrastructure of Africa, and for the challenges. And after all, we also have to see that blending materials locally is the better choice. If we think about getting some good pasta with some tomato sauce, certainly we can get ourselves in the supermarket, we can get ourselves a bag with a pre-mixed powder, which we just mix with water, and then we pour it over our noodles. In the same way as we do it with concrete, where we just buy a bag of cement. But we can also go to the local market, buy local quality food, which we can test beforehand. We can mix it according to our own rules, we can use our own spices, we can give it our own flavor in order to produce some noodles with an elegant and excellent taste. So which one of them would you choose? Certainly everybody would choose the tailored kitchen quality over the standard factory quality. But then if we think about it also in terms of cost, at the end of the day, the left model requires transportation, it requires processing, it requires people who have to do that work and who have to be paid. Which means at the end of the day, if we do the calculation on the bottom line, even the higher quality product, which is locally produced, locally blended, would be cheaper at the end of the day. And this is something we really have to understand. Also local economy is much better. Now, if we think, and this local economy aspect is extremely important, because people always think that more sustainable construction becomes more expensive for them, because they always think in terms of technology. which might need to be imported. But let's think about the global supply and value chains today for mineral materials like concrete and cement. Much of the intellectual properties, of the machines, of the processes, of the services, of the financing is in the hands of investors and big global companies in the global north. Which means if in Africa, for example, someone would build a house, this would probably be the cost of the house, but this entire fraction would finally flow out of the country into the hands of international businesses. And only this small fraction would stay within the local economy. Which means from a macroeconomic perspective, this might be very good because it creates jobs in China, in India, in Europe, in Northern America. It brings value back, it pays the Teslas of the CEOs and so on and so forth. So from a macroeconomic global perspective, this might be good. But someone finally has to pay this price. And you all know who is paying this price. These are the weakest in our societies, particularly the mineral business, we know this definitively. And these are the most marginalized people who do not pay this price in money, but they pay it in loss of future potentials in terms of loss of environmental health, in loss of physical health, and so on and so forth. So that's the price that is paid for the current global business models in mineral supplies for cement and concrete. If we would go to a local supply chain, the cost for the same house would be reduced, and a significantly larger fraction would stay within the local economy and create livelihoods and economic potentials. So that's the reason why everything has to be more localized in the near future. And Africa can play a pioneering role in that. Africa has a lot of challenges, without any question. And one of the challenges is urbanization. On the left side, you can see that the urban population in Africa grows 4 times faster than the urban population on average in the world. And we will see cities like Lagos or Kinshasa or Dar es Salaam with 70 to 80 million inhabitants in a couple of decades. That's incredible. These will be the biggest cities in the world, unprecedented. And of those urban buildings that will have been built in 2050, only 20% are already built, which means 80% have to be built over the course of the next 25 years. We cannot continue with business as usual. Something has to be done to make it better. And Africa is the place where this can happen and where it has to happen. This figure, I think, is very impressive. It shows the per capita carbon emissions in different parts of the world. And the red line, the dashed line, is achieved to reach the Paris climate goals. So we can see that the entire world is above threshold. So we all have to go down. We have to reduce our carbon emissions significantly. But sub-Saharan Africa is the only huge part of the world where the per capita carbon emission is significantly lower than the threshold. This is a perfect offset position to run innovation, to leapfrog technologies, and to right step into the future, to grow the economies without being wasteful in CO2 emissions like the rest of the world has been in the centuries before. And that is technically possible. So here you can see a figure where on the ordinate you can see the per capita CO2 emissions from cement use, and on the abscissa side you can see the per capita gross domestic product for many, many different countries. And we can see that when the per capita gross domestic product grows, we have something like a linear increase of the carbon emissions. But then when the per capita gross domestic product reaches about $22,000, then we can see that it is possible to also go down with the curve again by using better technologies, by having better regulations, and so on and so forth. But it is not mandatory, because it can also happen that you end up somewhere here, depending on where you are. But let's say this trend is a possible trend, and then we take a look at Africa. All African countries can be found within this square area, which means the per capita gross domestic product will fastly grow in the next decades. But this hump that we can observe here is mostly based on the fact that we linked cement consumption with concrete consumption. But today we do know that we can also build with good concrete without being wasteful in cement, which means this hump is not necessary. It's an old school technology hump, but it's possible to directly grow the economies fastly without being wasteful in cement. And that is the potential that only Africa has on this planet, and Africa has to lead. And that would also include the informal businesses. Like here, you can see a prediction until the year 2050 for Kenya, how per capita CO2 emissions could be developing if we would have a change in mindset, if we would use the best possible binders and we would use the best possible practices, including the informal sector, then the projected CO2 emissions by 2050 from here could be going down as low as here. We could even turn the trend and get lower with our carbon emissions in the future, if that would all be applied. And the potentials to get there in Africa are particularly bio-based materials. So I would like to introduce you to a few bio-based resources that could become potentially interesting for high-performance concrete. Chemical admixtures have reduced the carbon footprint of concrete significantly because they help to reduce the water that is needed to mix concrete, and this creates better workability, higher strength, and that needs less cement. But these chemical admixtures are based on crude oil, and this crude oil might be coming from Africa, but then it's moved to Asia, where it becomes a chemical precursor. From there it comes to Europe, where people mix it with water and with some dyes and some other admixtures, and then they export it back, and they have to be imported in Africa at a very, very high cost. Even though there are so many natural solutions that could replace in a much more sustainable way these petrol-based solutions. Cassava starch, for example, has plasticizing properties. Here on the figure on the left side, you can see that as a comparison to potato starch, where when you add more and more starch and you mix your fresh concrete, you would see that the torque increases, so it's getting thicker. But if you use cassava starch, consistency becomes softer and we can reduce the water content. Or acacia gum, it's also something that has a performance that is hardly better than the performance of polycarboxylate ether-based superplasticizers. And the interesting thing is that these acacia gums, initially they increase the torque, which means they are thickener, but when you add it at a certain dosage, they become a plasticizer and the torque goes down, the material becomes softer and has a very good consistency and helps to reduce water. So nature provides a whole lot of mixtures. So here we can see algae-based chemical admixtures which increase the static yield stress but don't have an effect on the dynamic yield stress, which means this is a good plaster. It sticks to the wall, but if you want to pour it, it's very soft. Or cocoa pot gums, which increase dynamic and static yield stress, which could be good for other applications like underground construction or like construction with slope. Or we also have this miscanthus gum, which significantly reduces the torque, which means this can be used as a super plasticizer with a very, very high performance. And then we do not only have organic admixtures that just give a slightly better consistency, but we can also replace cement by bio-based resources. And typically people rubbish this idea. So this is a figure which is often shown in presentations where people say, okay, this is the amount of Portland cement which we have to replace, and this is the amount of vegetable ashes that would be theoretically available. And since this is so small in comparison to the Portland cement, people say this doesn't make sense. But first of all, the order of magnitude of the vegetable ashes is comparable to natural pozzolana, to slag, and to fly ash. So I would not say it's a negligible amount, but then we also have to see that the overall Portland cement production number is dominated by China. But China has to import food, so there's no growth potential in agricultural products, which means the vegetable ashes are not growing in China. If we convert the same figure and look at it in different parts of the world more regionally, we would identify that in Latin America and the Caribbean, we could replace 10.3% of the actual cement production capacity with bio-based ashes. And I'm only talking about the waste of edible food production, like the peels, the skins, the cobs of the food we eat. In Northern America, it would also be 6.6%. In Sub-Saharan Africa, it would be nearly 5%. You cannot say this is negligible, but let's look at Africa particularly. The arable land use in Africa could be tripled. And for Africa, the average hectare yield is a third only of the world's average. So if the production would be only on the world's average and not higher, and all the arable land would be used, we could increase the amount of Portland cement production capacity up to 86.3% just by using the waste materials from food production. This is certainly a theoretic number, but if we only can activate 10% of it, we would already reach a lot. And these vegetable ashes can perform very well. This is a performance comparison of industrial mortar using microsilica in blue and using rice husk ash in yellowish. And we can see that the rice husk ash outperforms the microsilica even. And microsilica is very expensive on the global market, and rice husk ashes are wasted, are dumped away. So we have a lot of potentials with cassava, maize cobs, rice husk, groundnut ashes. And that is very important to understand, that these bio-based materials are the real future solution. The kickback of the initial figure that I've shown, that when a plant grows, it absorbs the CO2, and when it deteriorates, the CO2 is released again. So this moment, when a plant has reached its end of life, is the best moment to take it away and convert it into something, because that's the moment where it has captured as much carbon as it can. So much better than timber is to use other biomass materials to our construction materials at this point in time. And those fast regrowing crops are a very good solution, like cassava peels, maize cobs, sugarcane, groundnut shells, rice husks, and wheat char. And then certainly remember, some of these plants do not contain silica. Then they are not useful as a cement product, but we can still use it as a biochar. So before converting it into an ash, we can make a char out of it, a very lightweight material that captures carbon. So think of that figure again. So the plant is growing, and when the plant has grown to its maximum and then it is deteriorating, we can fuel it to convert it into an ash and make it a cement replacement. But that would be climate burdening, not because of the CO2, but because of the methane and because of the nitrogen oxides that occur during the burning. The cleaner we do it, the more we can minimize this number here. So that would be a pozzolanic ash. But if instead of burning it, we could hydrolyze it, which means we convert it into a char, and this char captures the carbon, which means the final char product is CO2 negative. If we put it into concrete, this CO2 is stored in concrete. But we have to be very careful with that, because it's the char that stores the concrete. So if there is a better use than concrete, it's a char that stores the CO2, which means if there is a better use, for example, in agriculture for this char, then we should also use it better here. But what we have found out is that the biochar can also have a positive effect on concrete. So here you can see that at different ages, with a small amount of biochar, we can increase the strength of concrete as in comparison to the gray reference value. And that is because the char distributes the pores in concrete in a better way. So even if we have more pores, they are better dispersed, and that increases the strength. But if we increase the strength even more, we are in trouble, and the strength goes down again. So someone is painting on my screen. That is not very beautiful. It's not me who is doing this. So maybe the person could stop this. So now let's think about this overall concept before I come to an end. So we do know that we can reduce the CO2 emissions by reducing the water content with organic chemicals. And solutions for these organic chemicals are sugar-based solutions, polysaccharides that can replace petrol-based materials. And then there's also bio-based pozzolanic materials that can help us to reduce Portland cement and concrete. So we have to make this as circular as possible in order to become greener. And here we have developed some technologies where we use bio-based wastes, which means agricultural ashes like cassava peels, and then first of all we boil them in order to obtain a superplasticizer. Secondly, we pyrolyze them, and that gives us energy, so we have an energy yield. It gives us a condensate which can be used in asphalt, and it gives us this biochar which could already be used as a carbon negative concrete aggregate. And finally, we use the biochar if it is rich in silica, and we burn it together with bricks so that we have the energy to produce the bricks. And what comes out after this process is an ash which has pozzolanic properties and can help to reduce the cement and concrete. And this way we use the byproducts entirely, we minimize the carbon emissions, we create circularity potentials, we create employment perspectives, particularly employment perspectives in the rural areas based on construction materials which are used for the urban growth. So that's a perfect synergy. But what is most important is that we use renewable resources here. Because we cannot do construction without fossil resources. But before we touch any fossil resources, we should always use renewable materials as much as we can. So scientifically, we have shown that we do have the relevant mineral oxides. We have established a process in which we can convert these mineral oxides into a structure. And with my colleague, Professor Olonade from the University of Lagos, we have even built a house made of cassava concrete. It's standing there. It doesn't distinguish from normal concrete houses. But what is missing are the ecosystems. So how do we get the materials from the farms into the process, and how do we get it from the process into the structure? And that is something we want to solve in the near future with colleagues also in Kenya, where we want to use an artificial intelligence to streamline all those small-scale supply streams of agricultural waste, aquacultural waste, industrial waste, process waste, and so on and so forth, which occur only on a small scale, so that they are not interesting for the cement industry. But we want to blend them using an artificial intelligence to always get out one big supply stream, no matter the season, no matter the fertilizer that is used, no matter the country where it's coming from, and so on and so forth. So it makes a lot of sense to use artificial intelligence for a mathematical problem. But at the same time, because we involve supply streams, livelihoods, human beings, different groups of people from different societal hierarchies, this requires also a lot of human intelligence. We cannot solve these problems in an adequate way and giving this into the hands of robots. We have to solve these problems as human beings. And this is something, and here I have to come back to the very beginning of the talk, where we have problems as engineers, because we always perceive ourselves as technicians, but we have a societal impact, and we have to get aware of that societal impact. And our biggest problem in the construction industry is that we do not communicate with each other, and that we all live in our own bubble. Like if I'm an investor, if I want to build something, I want to have a return on investment fast. If I'm an urban planner, my only job is to abide by the plans and not consider anything else. As an architect, I want to make it look very cool. I want to have an exposed structure, no matter the material demand. If the structure seems to overcome gravity, then we adore this building, but the reality is overcoming gravity, or appearing to overcome gravity, is wasteful in materials. As a structural engineer, a structural designer, I'm getting paid by the project volume. So I don't have an intrinsic driving force to tell anybody to reduce the materials. In fact, I gain if my structure is wasteful, and I calculate. As a material supplier, I market overperformance. When I tell my customers my material has a higher strength than the competitors' materials, then it's a selling point for me. But no one talks about the carbon emissions of it. And then as a contractor, at the end of the day, I just have to fulfill the timeline. So when it's getting tight, it can cost as much as it wants in terms of money or in terms of carbon emissions. I pay every price in order to abide by the schedule. And here we do not communicate with each other, and we are not willing to go for compromises. But we have to see that not a single of these individual bubbles can be fulfilled perfectly without compromising the bubble of anybody else, which means the most sustainable solution is somewhere between those bubbles. So we have to interact, we have to work with each other, we have to communicate, we have to understand the position of the other person, because all of those positions are justified to a certain extent. And we can only get there if we think back of those master builders I was talking about in the very beginning, that were more than architects and civil engineers. We need civil engineers in the future that also do understand the beauty of nature, that do understand history, that do understand the mechanisms of markets. But at the same time, technically and scientifically, they certainly have to understand particularly the nanoscopic scale, but they also have to understand the global macroscopic implications of their actions. And we can only get there if we get more conscious engineers. But here we have a problem, because our educational system is not made for evolution. We have those professors, the professors that teach to the students, and they do have all the knowledge and the wisdom which the students can learn. But professors are often no longer willing to change their mindset and adapt to the new times. The students are much more living in here and now, and in today's existing challenges, which means the students, they do have the nowness, the affinity to novel technologies and so on, which means the professors could learn a lot from the students if only they would. And here we can create a synergy between the professors who do have the knowledge and the students who have the nowness. And if we mutually learn each from each other, we can create this kind of conscious engineering that can converge the future perspective of our planet from the left perspective to the blooming perspective that we can see on the right side. And we have to start young. We have to start with the students right from the beginning and motivate them to get more conscious engineers in the future. They can learn standards over their lifetime, but they have to understand mindset, which is much more important. And when you start young, you can really have a huge leverage. And before I would come to the very end, I would like to explain this figure here. This is Efia. Efia is a girl in Jamestown, in Accra, which is a very neglected informal settlement. And regularly I go there. Become engineers or scientists. We will go to cement factories. We go we cast concrete. We paint walls and things like that. And I asked the kids to draw a picture of the city in which they would like their own children to live one day. And Efia, I did a course in cassava concrete with the girls before. Efia painted a cement factory, that's purple, this is the cement factory. I painted it right next to her house. And I asked her, do you really want to live next to a cement factory? And she smiled at me and she said, yes, it's no problem for me, because the cement factory is right next to a cassava field. So the concrete, the cement that is being produced here is green cement, and therefore I don't have any problems living next to a cement factory. And I think that's an interesting lesson to learn. And with that, I would like to thank you very much for your kind attention. Thank you.
Thank you very much, Dr. Wolfram, for this expose on the use of materials to replace cement and to make our world safer for us. Thank you very much. Please, let's put our hands together again. Dr. Wolfram. Now I would like to, before Dr. Wolfram started the lecture a while ago, one of the rapporteurs also came in, as Professor Bayoko. Thank you very much for coming. And I also can see our immediate past dean in our presence this morning, Professor Koya. You're welcome, sir. Good morning, sir. Please put your hands together for him. I will hand over the microphone now to the chairman of this plenary session to please take over proceedings from this.
Thank you. Thank you, our presenter and lecturer, Dr. Wolfram Smith. And we really appreciate your lecture, and there's quite a number of challenges you have even thrown to us. He has shown us how we started. And actually when he started and was telling us how we started, I was thinking probably all of us are civil engineers somehow. Since we have been building since the beginning, we build walls, we build roads. Now civil engineers are, again, he said they are the basis. They work in the background. And again, on that I was tempted to think, probably that's why we take them for granted. Because they are really there, so useful. We are in a building now. We have our roads, and those things are just there, so to say. So we take them for granted. But in his analysis, he has zoomed in. He talked about materials. And you see, those of you that are taking this introduction to materials, when he was talking about materials, structures, properties, I believe that will come to your mind. You need to understand properties of materials for use in building these structures. So, and in talking about that, he mentioned soil, concrete, steel, and timber as materials we use for construction. In that, he again zoomed in on concrete, because talking about carbon emission, you see, this climate change has to do with the emission of carbon dioxide. So he zoomed in on concrete, and has high carbon, yes, content, and because 50%, as he said, of all that has been produced, man has ever produced, 50% of everything man has ever produced is concrete. That's amazing. That shows us how important concrete is, how we cannot live without concrete. So he then zoomed in on this, that we have to look at that concrete. We have to look at it. So this is where the challenge is. How do we produce better concrete? Greener concrete. So he was talking of hybrid as opposed to composite materials. And blending. I am aware that in some of our universities, like here at Obafemi University, Abubakar Tafawa Balewa, ABU, University in Zaria, Ahmadu Bello University, Zaria, in the departments of civil engineering and departments of materials engineering, they have been doing some work on this blending thing, especially using bio-based materials like rice husk, maize, and things like that. Yes, there's quite a number of things that's being done in those departments. I'm aware of that. So it's like we're already into it, but we now have to go deeper. Go deeper. And if you look at our contribution, the Africa contribution to this CO2, you see that is very low. So he said below the threshold that was chosen there. So we have to do more research here. We have that advantage to do more research into this without necessarily contributing to the CO2 emission. So we give room, well, before that, frugality is important. So we have to be frugal. So the materials we use, we have passed the age of just using materials as we see them. We have to consider the economic aspect. So now we want to give room for contributions and questions. If you have, please raise up your hands and let's see, because we have